Okay, next, let's talk about how we study earthquakes. The machine that we use to study an earthquake and to record its motion and the amount of shaking is called a seismograph. Seismograph consists of a seismometer, which is the actual unit that measures the shaking, and then a way of recording a seismogram, which is the graphical representation of the shaking. So this would be our seismometer. And then the thing that it's recording on like the spinning disc, right, which is, they used to be discs or paper like that you would move along that would record the shaking as you go. This is the seismogram, or yes, excuse me. The actual readout of the shaking. These can be designed to measure shaking in several different directions. And this is sort of a representation of the analog way in which these measurements used to be made. So that, for example, in this setup here, this spring is going to move up and down and the mass is going to stay pretty much the same as the earthquake moves, but the whole apparatus around it is going to move in response to an earthquake. And as a result, because the seismogram is moving, but this mass is staying roughly the same place that it was, it's going to end up drawing lines representing how much the ground has shaken under the seismograph as it moves. The seismogram, as I said, was the readout of the earth shaking that is actually produced by the seismograph. And if we look at an example of what one of those looks like, this is a single earthquake here. And it records several different periods of shaking. Before the earthquake, you see no motion. And then once the earthquake hits this location, you start to see one set of motion, which is called the primary motion, called by primary or P waves. Soon after that, a secondary set of motion kicks in and starts a new round of shaking. So we've got primary, secondary. Often, these are just called P and S, and they represent two sets of different kinds of seismic waves that are hitting this location that are called P waves and S waves. The final thing to hit are the surface waves. Those travel along the surface, and so they don't move quite as fast. And these cause the most shaking here. You can tell it's the most shaking because the amplitude of the waves, the height of the waves is the highest. And this is what's going to cause the most damage near to an earthquake, at least. You can see that it can take some time, depending on how far away from the earthquake you are, can take some time for these to arrive. This is actually in minutes. So those waves can take some time to travel thousands of kilometers, and we can measure the earthquakes occurring at seismic stations that are thousands of kilometers away from the epicenter of an earthquake. In this image here, you can see the paths that these waves would take, starting at the focus of an earthquake, going to a seismograph that, as we can tell from this, is pretty far away on Earth's surface, right? So this whole surface is curved, so this must be thousands of kilometers away. The P and the S waves are waves that actually travel through Earth, through the body of Earth, inside Earth. The P waves travel slightly faster than the S waves do. So the P waves always arrive first, and the S waves always arrive second after the P waves. Finally, the surface waves travel the slowest. Their path has to be along the surface, and they arrive last. It is key to know that the P waves are the fastest, S waves are the second fastest, and then the surface waves, which is really a collection of several different types of waves, they move the slowest. So that always when you're looking at a seismograph, or excuse me, a seismogram, the P waves arrive first, the S waves arrive second, and then the surface waves arrive last. What are these different waves? What do they look like propagating through a material? Our P waves, we talked about first, so I'll talk about first here. P waves arrive first. They're P waves because they're primary waves. They are made of compression and tensional motion. So if we imagine this grid used to be uniformly spaced cubes like these over here, we can see that some of them are experiencing compression through this wave and some of them are experiencing tension. So there's a pushing and a pulling that is affecting these. So that's how these waves are propagating. P waves are push-pull motion, right? So we've got P means primary, but you can also think of the type of motion that it causes is push-pull motion. Like if you took a slinky and you pushed it in a direction, the wave is actually going to propagate through that slinky, or you could think of a spring. It's actually going to propagate through that spring in the direction that you push or pull. S waves are a little bit different. They're a little bit more like what you think of when you think about waves on an ocean, but they don't work exactly the same. They just kind of look the same superficially. S waves are either up and down or side to side motion. So the wave is still propagating in this direction, but the actual motion of any one given particle is actually up and down. And that pulls nearby particles up and down with it. There's a little bit more distance that you have to accommodate as you're moving this wave along. And that's why the S waves are a little slower than the P waves, because instead of moving directly in the direction that the wave is moving, these actually move perpendicular to that. They cause shaking up and down or side to side. S, secondary. To remember what these look like, I think side to side. So that's a way to remember P versus S waves. Surface waves are much more complex to draw, and they only occur on the surface. So we don't end up thinking about their sense of motion very much. But the deeper you go, if you go just tens of kilometers below the surface, you don't feel the surface waves anymore because they actually need that interface between the rock and the air above in order to propagate. So to summarize that, P waves, primary waves, push-pull motion. S waves, secondary waves, there are shear waves as well as a way to think about it. They're S-shaped and they move side to side or up and down. And those surface waves are the slowest, the most complicated, and cause the most shaking. We saw when we were looking at the seismogram before, that the amplitude of the surface waves was the highest. So how can we use the P wave motion of an earthquake to determine the direction of motion along a fault? Let's say we have a fault here. Here's that fault labeled. And let's say we don't know what direction this fault is going to move in, even though we see those arrows on here. Let's say we don't know starting out, and we've just set up some seismograph stations, 2 on either side of the fault. If we get an earthquake occurring here, some of those stations are going to experience a push first, so the rocks are pushing in those directions. And some stations are going to register a pull first, going to be pulling in those directions. If we put all that together, first let me point out what it looks like on the actual seismogram readout. So if you see a spike upward first, that is a push. It's experiencing a push first. And if you see a spike downward, then it's experiencing a pull first at that seismic station. If you put all those motions together, you can identify that the motion along this fault is in this direction. If we wanted to figure out, okay, is that left or right lateral strike slip motion, remembering what we thought about when we were thinking about deformation, we imagine putting a person on this, looking over the fault. And they're going to look over the fault and they will have seen everything move to their right. So that's a right lateral strike slip earthquake. So we can learn that just by looking at the pushing and the pulling of the different seismic stations located in a given area surrounding that earthquake. Another important thing that we can use is the time between when the P wave and the S wave arrives. The idea is that the P and the S waves move at different speeds. That means that if you are close to an earthquake, close to the focus or the epicenter of that earthquake, the P and the S waves haven't had a lot of time to separate from one another, so they're going to arrive pretty close together. But the further away you get from an earthquake, the further separated the P and the S waves will be, because the longer time that different speed has had to separate those two waves. So that means, working in reverse, that if we figure out how long between when the P and the S wave arrived, that time interval, here it looks like 1, 2, 3, probably 4 minutes is the time interval here. That would be representative of an earthquake at a particular distance. If the time between them was only 3 minutes or 2 minutes, that would be stations that are closer to the epicenter of the earthquake. And 5 or 6 or 7 minutes, those would be recorded PS intervals at distances further from the earthquake. We have plotted all of these on a set of graphs, and you're going to see some of these coming up in lab at some point. But the basic idea that is here we have distance traveled from the earthquake focus. And this is the time elapsed after the start of the earthquake. The P and the S waves move at different speeds. So for a given distance, the P are going to arrive first and the S are going to arrive second. Further away, P are going to arrive first, then there is a longer interval and the S are going to arrive second. Further away than that, the P are going to arrive and it's going to take a long time before the S arrive. So this distance, well, this graph distance here is the S minus P interval. We can tell this from reading our seismogram, and then we can find where on the graph this S minus P interval would plot, and then that will tell us, reading down here, what the distance was to our earthquake. You'll do a lot of practice on that in lab. We can also identify, if we have at least 3 seismographs put at different locations, we can tell exactly where an earthquake's focus occurred. Because given that information that we just gathered, the PS interval or the SP interval, I use them interchangeably, by reading the time separation between them when the P and the S waves arrive, we can determine the distance. But if you only had one station, say this station here, right, and you knew that the earthquake was 1,800 kilometers away, then it could have happened anywhere in this 1,800 kilometer radius circle. We're not sure looking at just one. Instead, we need 2 more seismic stations. Let's add in this second seismic station here. And this one was at 900 kilometers. So we draw a 900 kilometer radius circle. And using that, we can tell that the earthquake must have happened either here or here, because those circles are going to intersect in 2 locations. Adding that third station finally is enough. Okay, 3,300 kilometer circle. That's enough to finally tell us that this must have been where the focus was, because that's where all of the circles representing the distance to the earthquake, that's where all of them are consistent with one another. If they're not all consistent, that means something is wrong with our seismographs, or we are recording different events at each of them. We talk a lot about earthquake magnitude, which describes how much shaking occurred in an earthquake. And the old way to do it was called the Richter scale, which really only describes the amount of energy close to an earthquake and doesn't really give us a good sense of how much energy was released by that earthquake if we're looking at stations really far away. So we tend not to use Richter scale anymore. More often what we use is the scale called the moment magnitude scale. And that's the scale you see on this graph below. It tells us how strong the strongest shaking was related to how much energy the earthquake released in total. And it turns out that increasing your magnitude by 1 step is an exponential increase in the amount of energy released. It's about 30 times. So going from a magnitude 4 quake, to figure out how much energy would be in a magnitude 5 quake, you multiply that times 30. To go to the next step, again, it would be another times 30, and then another times 30. Give or take, it's actually a little bit more than that even. So that one increase in magnitude might not sound that much, but it is a 30 times increase in the amount of energy released. So strongest earthquake we ever measured was somewhere around a 9.5 or a 9.6 on the scale. Huge amount of energy released. This is kilogram equivalent of explosives. So if you're thinking like, right, a lot of times we talk about releases in terms of tons of TNT. So 1 ton of TNT is going to be 1,000. So if we think about a magnitude 9 quake, that would be 1.8 billion tons of TNT equivalent. That's a lot of energy released by a single earthquake. You can see some other famous earthquakes on here that these are some of the other strongest earthquakes that we've ever recorded, magnitude 9s at least. And there are certainly less than one of these every year. So this happens maybe once every 10 or 15 years, we get an earthquake that's that large. Whereas magnitude 8 quakes tend to happen about 1 a year. And magnitude 7 quakes, there tend to be about 10 of those worldwide every year. So you can see that the set of famous earthquakes is increasing as we go down to like a magnitude 8 or 7. And we would have tons and tons of earthquakes recorded all in here. It's just that they're not very famous because they didn't cause much damage, because there's less shaking, less energy released. Just to compare with other really powerful energy releasing events. So one of the strongest eruptions that we know of, certainly in recorded history, was the Krakatoa eruption. That's only equivalent to like an 8.6 or an 8.7 on the moment magnitude scale. So earthquakes can release even more energy than the strongest volcanic eruptions we've ever measured. And much more than even the largest atomic bombs we've ever detonated. So earthquakes, really powerful, release a lot of energy. So it's no wonder that they can cause so much damage to human infrastructure. Just to summarize that, because I want you to remember this. For each number in magnitude you increase on this moment magnitude scale, earthquake energy increases 30 times. It's a logarithmic scale, is what we call it mathematically. But you should know that it's 30 times the amount of energy in a magnitude 8 quake and in a magnitude 7 quake. So that's a way that we can measure the strength of an earthquake if we can determine how much energy it released. But if we just want to know the effects of shaking on humans and their structures, etc., the Mercalli scale is a way of quantifying how much shaking people and structures actually felt. And that's often a way where we can use the Mercalli scale where we ask folks how much shaking did they experience, or we can go out and look at the damage and then place it on this Mercalli intensity scale. For this, an earthquake will have certain numbers near the focus and epicenter and certain numbers further away. Whereas with the moment magnitude scale, an earthquake has a particular moment magnitude. It's not 8 at one place and 7 at another. It's just how much energy it released in total. So on the moment magnitude scale, it has an exact number. On this scale, the Mercalli intensity scale, the shaking is highest near the earthquake. So an earthquake might be 8 at one location and then 7 and 6 and 5 going further away. Let's just look at some of the examples of what the Mercalli intensity scale involves. So the first level that anybody is capable of feeling is a 2. So suspended objects may swing slightly. You're not causing damage from this, and only a few people are going to notice it. At a 3, you might start to get some shaking of parked cars. Some people will feel it indoors, especially higher up in buildings, because the buildings will amplify that shaking a little bit. At about a 5, you start to have some windows breaking. So you start to experience some actual property damage at a Mercalli intensity 5. Mercalli intensity 6, everybody's feeling that. You're going to have some slight damage to structures as well. and then going up 7, 8, 9. So like a 9 is damage is great in even well-built structures, and you have partial collapses already. The increase here is fairly severe. Once we get into 7, 8, 9, buildings can be shifted off their foundations. 10, 11, 12. 12 is just extreme damage, total damage. Objects are actually thrown in the air at that level. And so, of course, we're not going to have that intensity very often in any given earthquake. Lots of them will max out at a 6 or a 7. There was an example of a famous earthquake that actually happened near Memphis back in 1811. And only a few people were around in the area to feel it at the time. But those that did definitely indicated that there was a lot of shaking going on. And in fact, part of the Mississippi River temporarily flowed backwards as a result of this. If we look at the Mercalli intensity measured by human accounts of what happened at the time, then we can use it to say that it reached an 11 near the focus of that earthquake, and then a 10, a 9, and 8 further away. So there was some severe damage caused by this earthquake on any human structures that were in the area. Luckily, this wasn't built up yet at 1811, but you know, if this had happened 100 years later, it certainly would have caused extreme devastation. So there is a risk that another earthquake could happen in this New Madrid seismic zone in the future. Some of the shaking was even felt as far away as New York City from this. And certainly a lot of shaking was felt in Knoxville. So it's something to be mindful of, that this seismic zone in the New Madrid area exists.